Hi, everyone. Welcome to NextGenInfra.io. I'm joined today by Richard Bonner from Accelsius, a company that's at the forefront of the liquid cooling revolution in data centers. As AI and high-density compute are pushing thermal limits beyond what air cooling can handle, liquid cooling is, of course, emerging as not just a nice-to-have, but a necessity. Accelsius's NeuCool platform is now being showcased at Equinix's Co-Innovation Facility, and it promises a scalable, energy efficient, and safe path forward. So, Richard, great to have you. Let's start out with why liquid cooling is now mission critical for data centers.
Well, this AI challenge that's in front of us is demanding hardware that is really pushing the limits beyond what traditional air cooling and even current state-of-the-art liquid cooling can handle. Um, I think for a long time, maybe 20 plus years, air cooling was enough, and I think the uh, all of the partners involved sort of pushed towards these 10 to 40 kilowatt racks with 400 watt processors. But AI is demanding today 700 to 1,000 watt processors over 100 kilowatts a rack. And we're seeing from the NVIDIA CEO and other uh, tech leaders, they're going to be pushing 600 kilowatt racks, 2,500 plus watt processors. It's six times what air cooling could do. It's pushing the limits of what liquid cooling can do, and they need something better. So we're
Yeah.
developing that next generation of direct-to-chip liquid cooling technology, leveraging the benefits of two-phase cooling physics, which is just it's the next level of what you
Okay.
need to cool this hardware.
Yeah. Explain a little bit more about that. What makes you guys different?
Right. So traditionally, with direct-to-chip liquid cooling, they're bringing water-based mixtures over a chip. That water comes across, simply removes the heat and takes it in a very single-phase mode. Right. It's just straight up liquid cooling. With two-phase cooling, we bring a fluid that's near its saturation point, and as soon as it hits the chip, the heat of that chip causes the fluid to boil, and that vigorous boiling process provides a natural mixing that ultimately is taking that heat off the wall much more efficiently than that just natural single phase mode. A second part of actually there's several benefits, but a second part is has to do with that boiling process as well. One is boiling removes more heat per unit of flow. So with the same amount of flow, you can actually absorb more heat in that vapor than you can just by simply warming liquid. And finally, there's another part that I think is missed a lot. It's one advantage that's missed a lot by the community. It's thermal uniformity. So when you bring single phase fluid over a chip, it starts cold and ends up warmer, usually about 10 degrees warmer from the start of the chip to the end. And that's seen by the chip, right? The chip experiences different thermal expansion, different thermal stresses because of that change in temperature. With two-phase cooling, our fluid doesn't heat up. It actually stays at the exact same boiling point. The only thing that happens is the liquid changes to vapor. That's where that heat absorption is seen. But that's a huge benefit to the chip because now the chip is at the same temperature all across it. The thermal stress is near zero across that chip compared to single phase cooling.
You're talking about the surface of the chip itself as the cooling liquid goes across.
Yes, exactly.
Yeah. And how does the fluid get returned to its initial state then back to liquid?
Right. So as you leave the chip and make your way back to the manifold that accepts the fluid coming off the server, ultimately that's brought back to a condensing heat exchanger. And I'll point out that that condensing heat exchanger is actually the same form factor as the heat exchanger used in direct-to-chip single-phase cooling, right? So with direct-to-chip single-phase cooling, basically you take hot fluid and make it cold again. In our solution, you take vapor and return it back to liquid, and then the process repeats.
Okay, and this two phase, how does it compare in terms of the thermal efficiency, then the amount of heat that can be removed?
Right. So typically the efficiency improvements in terms of pumping power, it's very similar to single phase water, maybe a little bit better. Where most of the efficiency improvements come across is through that improvement in thermal performance. So by enabling colder chip temperatures, now you can start with a warmer fluid to begin with. And that's where the energy efficiency comes, because if you have warmer fluid, warmer facility water in your system, in your data center, now you can, for instance, enable more free cooling, where you don't have to run your energy intensive compressors to make the fluid cold relative to the ambient environment. Maybe you need less water. Maybe you can even run your facility water hot enough that you can recover some of that heat. I think by heating nearby homes, buildings, heating swimming pools, but ultimately most of those major efficiency improvements come from that better thermal performance that really starts at the chip.
Okay, and so then the waste heat gets transferred over to uh, another heat exchanger to other liquids to.
Yeah, that's true. That's true. Right? I mean, our solution, the way it works is it's basically taking the heat off that chip very
Mhm.
efficiently, and then it's putting it into a facility water loop, maybe even putting it into your data center's existing air system, its existing air handling system. But because it does it more efficiently,
Right.
whether it's running your data center with warmer air or warmer facility water, that ultimately cascades into more energy improvements as a
Okay.
whole for the data center.
Okay. One more technical question before we jump into the Equinix news, and that's just the liquid itself that you're using, or the solution that you're using. Tell us about it. Does it introduce any other complications for the data center operator?
No, I would say no. So, but I'll say it, but that's not obvious. So the fluids we use are refrigerants, and as such, if you designed a system um, without the data center operators in mind, you could come up with a system that needed HVAC service technicians or some other skill that they might not have today. But in our system, we basically very early in the design process, we saw that being a challenge. So we've made our system with lots of serviceability features. For instance, if you need to swap out a pump, it's all on blind mate quick disconnects. You need to swap out a pressure sensor, that's similar. So the end result is that you don't need an HVAC certified technician to service any of our components. You can use the operators you have today. The only time you would need uh, an HVAC certified technician would be at deployment when you're doing that initial charge of refrigerant. But we, of course, help handle that part of the process. And then
Okay.
I'll also point out that in the server itself, we're using cold plates that, if you didn't know any better, look the same as other direct-to-chip liquid-cooled cold plates. So whether you're replacing a cold plate, swapping out a TIM, pulling a server out, and pulling on quick disconnects, all of those operations would be very natural to the operators who are doing single-phase water today.
Okay, great. Now, could you tell us about what's going on with the Equinix test or trials?
Sure. I mean, Equinix, obviously, they're a very large data center, very well-known name. Um, we've been designing and building and testing our products in our lab, which has a very representative chiller system in the lab to work out the kinks in our product. But as you know, each data center is a little different. Every facility water system is a little different. Do they bring the fluid in from the roof, the above the rack? Do they bring it from below through the floor? What are the connections like? They're all a little different. I think by getting in and deploying our solution, whether it's an Equinix's Co-Innovation Facility or some of the other facilities you've seen some of the press releases on, it just shows that we're able to take our product that was developed in our lab and adapt it nicely to fit in all these different real world data centers that are out there. Because again, they're all just a little bit different.
Richard, I understand that you guys have participated in the ARPA-E program. What is that, and what role have you guys played?
Yeah, yes, we have. So maybe 2 or 3 years ago, ARPA-E through the Department of Energy launched a program called COOLERCHIPS. And that program is designed to basically push the next generation thermal architectures for cooling, right? To make sure we were ready for this sort of AI problem in front of us. We were, as Accelsius, we were not in the program initially, but we were invited as a startup and as a guest lecturer to some of the recent meetings. And ultimately, we ended up latching on to a program through UT Arlington, where they have some two-phase cooling, some very advanced evaporator research that they're performing, and we complemented. We were I guess asked to help out with their program because some of the CDU developments that we had undergoing naturally complemented their work. So we've gotten involved. We've now delivered a CDU to UT Arlington, and they're testing some of their cold plates with our CDUs, and it's been a great partnership. There's a lot of great networking that has happened for us. A lot of great learning, great educating. I'll also say through the COOLERCHIPS program is actually where we met Equinix for the first time. So one of the Powell brought us from Equinix brought us into this cooling innovation center based upon a discussion we had with them at lunch. So we had lunch at one of the meetings where I was giving a talk. And next thing you know, I mean, I guess it's been about 8 months now, but from the time we met to the time we launched this, but it all started through that program. So the COOLERCHIPS program, I mean, it's been a great program, very well recognized, a lot of great researchers involved. So I think being involved in that program has helped us not only with the UT Arlington effort, but also uh, getting us into Equinix and other opportunities that have come out as well.
What's next? I mean, we're all seeing this data center race going on, and people talking about having, I don't know, up to 1 million XPUs in one facility. For Accelsius, what's next?
That's a great question. I think I'll address it in the near term, which to me is the next 18 months and maybe beyond. I think in the next 18 months, we're going to see many of our products naturally grow in size. So for instance, if we're doing a 250 kilowatt CDU, you'll probably see a 500 or a 1 megawatt CDU that looks very similar form factor, similar size. We'll package it tighter, we'll put larger pumps in, but we'll get to those levels in the next 18 months. And I would say similarly, on the cold plate side, we've hit 4,500 watts. I think you'll see natural extensions to what will be required in the next 18 months. What happens beyond that, I think, is exciting. We're not really sure. I mean, when we look at these 1 megawatt plus racks and what that means holistically in a data center, there's a lot of things that need to happen around that 1+ megawatt rack. You need networking, you need power, and you need thermal. And I think that's being, I'll say, co-engineered. I think all of those different entities are coming together to figure out what does that 1+ megawatt rack look like. And I think once to make that work, I think you are going to see changes in architecture. I certainly think two-phase cooling and its all the advantages that I've talked about are going to be there. They're going to help enable that next architecture by using less flow rates, that the increased thermal performance at the chip. Those are all going to be required. But what it looks like is it's unknown at this point. I think there's a lot of development that has to happen. It has to happen pretty quickly to be ready for what happens 2-3 years down the road.
Awesome. Yeah, it's quite a race, so we'll keep watching. Well, good luck to Accelsius, and hope to hear more good things from you guys soon.
Thanks, Jim. Thanks for the opportunity.